From this lecture, we will start a new chapter, that is a small signal analysis of BJT. We have already completed the construction part, the characteristics part, and the biasing part of transistors. In this chapter, we will examine the AC response of transistors, and for this purpose, I will introduce different frequently used transistor models. I will introduce different transistor models, or you can say different transistor equivalent circuits. In AC analysis, the first thing we need to do is to decide whether to use a small signal or large signal technique. In this chapter, we will stick with small signals and we will study large signal analysis in the separate chapter. The large signal amplifiers are called as power amplifiers. The large signal amplifiers are called as power amplifiers. There is one separate chapter on power amplifiers. Now we will talk about the operating point in small signal analysis. By using this small signal, we do not have to worry about the operating point, because if we use the large signal, the base current IB will also increase. If we use the large signal, the base current IB will also increase, and we already know the collector current IC is equal to beta times the base current, neglecting beta plus 1 ICBO, and if IB increases, this implies the collector current will also increase, and when collector current increases or collector current changes, the operating point, that is Q point, will also change. And this is something which is not desired. We do not want the operating point to change or shift, but we do not have to worry about this condition, because this condition arises in large signal analysis. In a small signal analysis, Vs is small and IB will not change much, and hence IC will also remain constant and the operating point will not shift. So we can define this small signal as the signal having magnitude sufficiently small to keep the transistor in active region. This is the definition of a small signal. I will repeat it again. The small signal is the signal having the magnitude sufficiently small to keep the transistor in active region. Now why we want to keep the transistor in active region? Because we want to use the transistor as an amplifier. And if you want to use the transistor as an amplifier, then it must operate in the active region, because in active region we have the amplification of the weak input signal. In active region, the collector base junction is reverse biased and the emitter base junction is forward biased. The last thing is the total response. The total response is equal to DC response plus the AC response, and we can definitely analyze the DC response and the AC response separately. We have already completed the DC response part of the transistor, and now we will complete the AC response. And for this we must have clear idea about this circuit. This circuit is BJT amplifier circuit. BJT amplifier circuit. The portion of the circuit inside the rectangle is voltage divider bias. We have already completed voltage divider bias in the previous chapter. Actually we have this whole circuit, but in DC analysis we only have to consider the portion of circuit inside the rectangle, because C1 and C2 will act as open circuit and the portion outside the rectangle will not be included in the DC analysis. But in case of AC analysis, we need to consider this portion and this portion of the circuit outside the rectangle, because all the capacitors will act as short circuit for the AC signal. I will explain why capacitors are acting as short circuit for the AC signal and they are acting as open circuit for the DC signal. Capacitors C1 and C2 are called as coupling capacitors. I will write this down. C1 and C2 are called as coupling capacitors, and capacitor C3 is called as bypass capacitor. Bypass bypass capacitor. All the three capacitors C1, C2 and C3 have very high values of capacitance, and because of this they behave as short circuit for AC signals. And Xc, the reactance of capacitor, is equal to 1 by 2 pi Fc, where F is the frequency and C is the capacitance. If we consider the DC signal, the frequency is equal to 0, so reactance is equal to 1 by 0, which is equal to infinity. So all the three capacitors will act as open circuit, because open circuit is having the infinity resistance, and this is for DC signal. In case of AC signal, frequency is not equal to 0, and I have already told you the capacitance for all the three capacitors are very high, and because of this the expression of reactance will have some large value in the denominator, and Xc is nearly equal to 0. So for AC signal, the reactance offered by the three capacitors is nearly equal to 0. The reactance is the resistance offered by the capacitor or the inductor. Now I will explain why we call C1 and C2 coupling capacitors and why we call C3 as bypass capacitor. C1 and C2 are called as coupling capacitors because C1 is coupling the previous stage with this circuit and C2 is coupling the next stage with this circuit, and they are important because we do not want the DC voltage from this stage or from this stage to interfere with the DC biasing voltage, because this will change the operating point. The DC signal from this side and the DC signal from this side will see C1 as infinite resistance and C2 as infinite resistance, and they will not interfere with VCC, and the operating point will remain constant. And as they are coupling the previous stage and the next stage, we call them coupling capacitors. C3 is called bypass capacitor because it bypasses the AC signal. The AC signal will have two different paths. The first path is having resistance Re and the second path is having the capacitor C3. There is some resistance because of resistance Re in this path, and C3 will offer zero reactance for the AC signal. So the AC signal will choose this path, and you can see resistance Re is short circuited because of capacitor C3 in case of AC signal. Now why we are so desperate to short circuit the resistance Re? The gain reduces because of resistance Re, and if we short circuit the resistance Re, the gain will increase. I will explain why gain reduces because of Re in the coming presentations, and this is all you need to know about the BJT amplifier circuit. C1, C2 and C3 are very important, why they are used and how they act as open circuit for DC signal and how they act as short circuit for the AC signal. Now to find out the AC response, we need to do two things. The first thing is to find out AC equivalent circuit. And once we have the AC equivalent circuit, we need to replace the transistor with its equivalent model. We need to replace the transistor with its equivalent model. The equivalent model, or we can say equivalent circuit. In the next lecture, I will explain how to obtain the AC equivalent circuit, and after this we will see different equivalent models or equivalent circuits for the transistor. This chapter is very important in analog electronics course, and you will definitely have questions in your exam from this chapter. The coming presentations are very important. Please try to make notes from this lecture so that you may revise them before your exam. This is all for this lecture. See you in the next one.